All right, so let's look at this practice problem we've got here on heating curves. Let me get this thing squared away. There we go. All right, and we'll go with blue. All right, so the heating curve problems are pretty straightforward. I just wanted to work one to make sure that we had one for you to see. So the question wants us to calculate the enthalpy change associated with converting 1 mole of ice, so solid water, at -25 Celsius to water vapor at 125 Celsius under a constant pressure of 1 atmosphere. So some things we're going to need for this. We're going to need the specific heats of ice, water, and steam, the three phases of water. We're going to need the delta H of fusion and vaporization, our enthalpies of fusion, our enthalpies of vaporization. And it would be helpful to have a heating curve, right? It would be helpful to be able to visualize how this phase change is going to take place. So in order to accomplish this, we're actually going to employ Hess's law. We're going to add, we're going to sum the parts in order to find the enthalpy change of the whole. And so we're just going to jump right into this. So I'm starting with ice at -25 degrees. So that's right here at point A. And we're going to go from A to B first, because basically what we're going to do is we're going to sum each leg of this graph. So in AB, delta H is going to be equal to, well, we know we have 1 mole of ice. We need to convert that to grams, and it's about 18.0 grams per mole for water. Okay, and we needed to convert it to grams because our specific heat is in joules per gram Kelvin, right? We need that there. And we're at 25 Kelvin as far as the temperature change is concerned, right? So delta T here is 25 Kelvin. Now, hopefully, you remember that we're basically using the MC delta T equation here. And hopefully you remember that a degree change in Celsius is equivalent to a degree change in Kelvin. So to go from -25 at A to 0 at B is a change in temperature of 25 degrees. And in this case, we get 914 joules. Now, I'm looking ahead. I know I'm going to be adding enthalpies of fusion with kilojoules. So I'm just going to go ahead and convert that, divide by 1,000, and I get 0.91 kilojoules. All right, that's what we'll say. So there's AB. Now, for BC, right, this second leg, I don't have a temperature change. And so we can just use the molar enthalpy of fusion directly here in order to calculate this leg. So BC is delta H is going to equal 1 mole, 1.00 mole, right, of ice, right, melting to form liquid. So I need to use the fusion modifier there, the fusion value of 6.01 kilojoules per mole. Mole is going to cancel, and I'm left with 6.01 kilojoules. Convenient, right? So now I have A to B. I've done B to C, so now I need to do C to D. All right, so I'm looking at that leg of my problem. I'm going to go back and I'm going to use the exact same setup that I did in AB. So I still have 1 mole at 18.0 grams per mole. All right. And now I'm using the specific heat of water because in this second phase, I have liquid water. So 4.18 joules per gram Kelvin. All right. And my temperature change is obviously 100 degrees Celsius, so 100 Kelvin, right? I'm going from 0 to 100. That's my temperature change. So final minus initial is a positive 100 value there. And that's going to give me 7520 joules, which we're going to go ahead and convert to 7.52 kilojoules. All right, I've made it from A to D. Now I need the leg DE, right, that segment of my graph. Again, I'm just back to using the enthalpy. So I have 1.00 moles. I'm going to multiply it this time by the delta H of vaporization, so 40.67 kilojoules per mole. Mole cancels out. I'm left with 40.67 kilojoules. I'm going to need that number. All right, and then I'm finally at E, and so I need to go to F, and I need to get EF, which is again going to look like CD, and it's going to look like AB. So I have 1 mole. I need to convert it over to grams. And I realized that in this instance, right, I could just start with 18 grams per mole. But I'm showing you this step because in the event that you don't have 1 mole, you're going to need to remember to do that first part. So make sure that if you're doing a problem that has more than 1 mole, that we adjust for that. So because I'm on the steam leg, I'm using the specific heat of steam, which is 1.84 joules per gram Kelvin. I have a 25 Kelvin change in temperature because I'm going final is 125, initial is 100. So 125, right, minus 100. That's going to be delta T. That's going to give me 25 Kelvin as my temperature there at the end. And that gives me 830 joules, which we're going to convert to 0.83 kilojoules. So now I've successfully moved from A to F, right? And all I need to do now is sum my parts. So delta H is going to equal 0.91 plus 6.01 plus 7.52 plus 40.67 plus 0.83. And I can add all these because I've converted them to kilojoules already, so I'm adding my like terms, and this is going to give me 56.0 kilojoules equals delta H, the change in the enthalpy for that phase change. All right. Now, every time you do one of these, they're this simple. The issue that kids run into is they forget, hey, I have 2 different little equations that I'm doing here. So sometimes if I'm doing just these level portions of the graph, all I need is delta H equals moles times the delta H of fusion. Okay, and the reason I don't need temperature here is there is no temperature change during the actual phase change. The slope there tells us that temperature is not changing, right? There's no change. And then for my, C to D regions, my regions with slope, I have a change in temperature. So I'm really just using this, right? Q equals MC delta T, right? Where I have mass, the specific heat, times the change in temperature. And we know that Q, right? Q and delta H can be used interchangeably there. Just remember for mass, I need to convert moles if they just give you moles over to grams. So I use the periodic table. All right. So hopefully that helps you step through that problem. If you have questions, let me know.